Hello, chemistry students. It's Mr. Gopal here with a lesson that talks about the intersection between chemistry and math. Often we have to use a lot of math in order to understand what's happening chemically in the world, and this lesson is a prime example. Specifically here, what we're interested in is calculating the average atomic mass of isotopes of an element. When I say isotope, I'm talking about a version of an element with a particular amount of neutrons. And you might be surprised to hear me say the word version. The reason why I'm using that is very intentional, and that's because for every element known on Earth, we have many different isotopes. That is to say, we have multiple versions of that element, each of which has a unique amount of neutrons. So carbon-12, for example, is a specific isotope of carbon, and that's the most abundant kind. If we look over here at the periodic table, we can see carbon is in the key at the top, so we have a zoomed in version. That's why I chose it. And we can see that its atomic mass is 12.011. Now, I can tell you, because I know how to calculate the atomic mass, that means carbon-12 is probably our most abundant version of carbon. We have carbons 13 and 14 as well, with 7 neutrons and 8 neutrons respectively. All right, carbon-12, what we have to do is we have to take the integer version of the atomic mass. If we cut off the decimal, that would just be 12. All right, and then we subtract the atomic number, which is the number of protons. That's 6. 12 minus 6 equals 6. And so we have 6 neutrons in carbon-12. And because the atomic mass is so close to just 12, we know that carbon-12 happens to be the most abundant version of an atom. So we have multiple versions of all of our atoms, and those versions are called isotopes when they have different numbers of neutrons, somewhat like we have different varieties of rocks. So if we look at this picture, the rocks are all different sizes. We could pick up some with our hands or with a shovel, but we might need a mechanical scoop, one of those caterpillars, which is basically a vehicle with a giant mechanical shovel attached to it that we can operate with controls to pick up boulders. All right. Now, all those rocks might have the same chemical composition essentially. All right. They might behave the same way when subjected to different chemical processes. However, they're of different sizes, much like carbons 12, 13, and 14 are of different sizes as well. When we talk about atomic mass, it's so important because neutrons, as we've learned in previous lessons, are the most massive of the 3 subatomic particles. So to review, inside the atom, we have subatomic particles. For now, those are protons, neutrons, and electrons. Of the 3, neutrons are the most massive. They're slightly more massive than protons, and both protons and neutrons are far more massive than electrons. So adding a neutron, or 2 neutrons, or 3, to create a new isotope of an element will dramatically change the atomic mass. And now we want to talk about how to calculate those. And in order to do that, I've made a handy guiding document. So if we look at this, we need to talk about weighted averages. So when I say atomic mass, I'm not talking about mass number. In previous lessons, you've learned to calculate the mass number based on having an element, then a dash, and then a number. Okay, so if I had carbon-13, just grab my stylus here. If I had carbon-13, I might represent it with C-12. I know that there are 6 protons in carbon, right, and 12 neutrons. All right, so in order to figure out the number of neutrons, I have to do that mass number, which is 12, minus the atomic number, which is 6, and I get 6. But if I had carbon, say, sorry, I'm going to make that more exactly at 12. If I had carbon, say 13, I would follow that same process, except the number that I'd be subtracting from would be 13 instead of 12, which would mean that I would have 7 neutrons, and so on and so forth. Now, a basic way to think about atomic mass is, let's say that I gathered all of the carbon on Earth, all right, and I figured out how much of it was carbon-12, and how much was carbon-13, and how much was carbon-14. Then I could calculate what I call a weighted average. This is a weighted average because it's not a simple average. The way that a simple average might work is if I took 3 tests, let's say, and I got an 81 and a 92 And let's say I didn't do so well on the last one. I got a 70. All right. If I wanted to calculate the simple average of those three tests, I would add them together. And I would divide by 3. And that would give me, let me just calculate for us real quick. That would actually give me an 81. I did not do that by design, but I can see how it worked out based on the difference between 81 and 70 and 92 and 81. Anyway, that's a simple average. All I do is I add up all of the items, the sum of all the items that I have, and I divide by how many items I have, and that's how you construct a simple average. When I do a weighted average, that means that certain things weigh more or have a greater weight in the average than others, all right? And so I'm going to demonstrate that, but first I'm going to give you an analogy. Let's say that you're taking this chemistry course for a grade, all right? We know that not all assessments or assignments are created equal. You might have a class participation component and a homework component, and then a test or exam component, quiz component. And each one of those is weighted differently depending on what your teacher decides. So class participation might be worth, say, 10%, and homework might be worth 25. Let's say that that was the case. And the remaining, make sure I get this right, the remaining 65% would be tests. So that would mean if you had a rough day in terms of participation, you weren't sure, so you didn't really answer any questions, and your teacher gave you a low class participation grade, that might not matter a lot. On the one hand, class participation is only 10% of your grade. On the other, you get a class participation grade maybe every day. And so having one bad day might not dramatically affect your grade. However, if you had a bad test grade, if you had a bad day on that, that's 65% of your grade. So now that bad test grade is going into your test average, and it's going to make a much larger difference in your overall grade. Now, I'm not saying that's fair, and hopefully your teachers are being equitable when they observe your growth as a participant in class and your diligence with doing your homework, and you won't necessarily, your grade won't necessarily live or die based on having one bad test. All I'm trying to illustrate is the same thing goes when we have atomic mass or when we want to calculate it. So let's say that we have a sample of copper, and we have two different isotopes of copper in that sample. We've got copper 63, which is represented by this Cu-63, and then we have copper 65, represented by that symbol Cu-65, all right? And let's say that 69.17% of my sample is copper 63, and the other is copper 65. And I want to figure out the average atomic mass of this sample, okay? So I've got my two isotopes, but I also have my two percentages. And so we need to do a calculation involving both their percentages and the isotope value, all right? Let's start with the percentages. The first thing that we need to do is convert percentages to decimals. I'm sure you've done this before. If we want to take 50% of something, we divide that 50 by 100. That means moving the decimal point 2 times to the left. We get 0.5, and then we multiply that 0.5 by whatever the value is that we want to find 50% of. It's much the same with more complicated percent values. If I take 69.17 and I move the decimal twice to the left, I'm going to get 0.6917. And if I take 30.83% and I do that, I'm going to get 0.3083. That's all I need to do in step 1. Just convert percentages by moving the decimal point to the left 2 times. Pretty simple so far. Now what I'm going to do is I'm going to take those converted values and I'm going to multiply each one by its partner isotope, let's say. So we know that 69.17% of this thing, this copper sample, is copper 63. So I'm going to take my 0.6917 and I'm going to multiply it by 63. And this is the decimal that I get, 43.5771. And I'm going to do the same process with my copper 65 and my 30.83% that I've converted to a decimal. So I have 0.3083. and I multiply it by 65, and I got 20.0395. Oops, I see a little problem here. I wrote 63, I meant to write 60. Oops, that one's right. I meant to write 65 down here. There we go. So I've multiplied them and I've gotten the products. Those products, all I need to do is take them and add them together, and I'm going to get my weighted average, or my average atomic mass for copper. So here you have it on the final line. I take the first thing that I calculated, which is 43.5771, and I add it to the second thing, which is 20.0395. And I have my final answer, which is 63.6166. And that is all there is to it. Now, the one thing that you might have to do in a Regents problem is you might have to round this off. So if we look back at the periodic table, we can see that we usually take, well, it's not uniform, but most of the time we have our atomic masses to either 2 or 3 decimal places. So if I rounded this to 2 decimal places, I would have 63.62. That's with 2 decimal places. If I rounded it to 3, I would have 63.617. In each case, I'm rounding up because the number after the amount of decimal places that I want to preserve is a 6, and that means round up. So now that we've had a little bit of practice doing this with a model, let's see if we can go through one of the examples in the lesson. So I'm going to shoot all the way down here. And let's think about this question. We have 4 naturally occurring isotopes of sulfur, S32, 33, 34, and 36. Each one has a different natural abundance, and each one has a different atomic mass, all right? And those atomic masses are a little bit more complicated than the ones that we used, because they actually have these decimal values instead of a straight up mass number like 63 or 65 like we had in the previous problem. But the setup is the same. The first thing that we want to do is we want to convert each of those percentages into a decimal value. So I'm going to write it here in a little chart. We've got S32. And if I move the decimal place twice for its natural abundance, I change that from 94.99 to 0.9499. And now let's do that quickly with the other ones. S33 is 0.75%. I have to move the decimal point twice, even though it's a fraction of 1%. So when I move it twice, I get 0.0075. All right, that one's a little bit trickier. Moving on to S34, I convert 4.25%. Again, I move it twice, and I have 0.0425. Finally, I do it with S36. I have 0.01%. There's barely any of that in the world. And so if I move the decimal twice, I have to be careful about counting my zeros. I get 0.0001. A good rule of thumb is if it's a fraction, well, if you want to check it again, a good rule of thumb would be to just move the decimal point twice back and see if you get your original number. So if I move it back, we can see in each of these cases, I'm moving it twice to the right to restore it to its original version, its percentage version. I can see that I'm getting the numbers back. So I've got the correct decimals, and that is the end of my first step. The next thing that I need to do is take those and multiply them by their corresponding atomic masses. So I'm going to do that here. I have to multiply the first one by 31.972. The second one by 32.971. The third one, oops, forgot my multiplication sign. Third one by 33.968. And the fourth one by 35.967. Let me just add in again, I left out my multiplication signs. select this and make sure that it's exactly lined up here. Great. And now I can go up and I can get my values. So if I have 0.9499 multiplied by 31.972, I want to get this number. And for now, I'm not going to round them off. Don't forget that we're just going to round off at the end. So for now, I'm just calculating products. I'm not going to round off until I add all these together to avoid error in my calculation. Oops, 0.0075 times 32.971. 0.2472825. And I definitely suggest that you write all this down as you're doing it along with me to practice doing the calculations right, moving decimals right, preserving answers correctly. It can get very tricky when you have complicated decimals because they're not easy to remember. This one's going to be 1.44364. And then the final one, that's going to be 0.0001 times 35.967. That is 0.0035967. Okay, final step. I'm just going to take all of these and add them together. And when I add these four pieces together, let's see what we get. 0.0035967 plus 1.44364 plus 0.2472825 plus 30.370228 equals, and here is my final answer. I'm going to write it right below here, 32.064722. All right. Now, how can I tell that I got an accurate answer? Well, we know if almost 95% of this sample is made out of sulfur 32, then I should have an answer that is close to 32 AMUs. And I do, it's just slightly above it. Now, the final thing that we can do is we can round this off. If I round to 2 digits, that would be 32, 2 digits after the decimal, that is 32.06. If I round it to 3, well, that's going to be 32.065 because the 7 after the 4 rounds the 4 up to 5. I hope this has been a good introduction. I hope the document helps you. Do keep the document close and make sure that you're following the steps very accurately and methodically as you do more problems like this. That's all, but hopefully you got a lot out of this. In addition to doing the calculations, hopefully we shed a little bit more light on the idea that there can be multiple versions of an element called isotopes in the world. And what we're reading when we read these decimal atomic mass values on the periodic table are average atomic masses for based on the weighted average of all of the known isotopes and their natural abundance in the world. This is Mr. Gopal signing off. I hope this has been helpful, and I will talk to you soon.